Thank you very much for inviting me. So, who are the undergrads here? One. Oh, okay. And then who are the grad students? Okay, that's good. All right. So I was told I should try to keep this, easy, colloquial talk or whatever. So I'm going to be talking about sort of kind of a range of things related to liquid crystals. And the talk may seem long. It's not going to be quite that long. Some things I'm going to skip, on purpose. So I don't know. I mean, you have Giordano here. Maybe he's explained how liquid crystals work, but I will give my own take on it. So liquid crystals are sort of a particular type of molecule. And there's like thousands of varieties of this. And so here they're kind of idealized as an ellipsoid, an elongated ellipsoid. And so because of that elongated shape, it gives them some nice properties, particularly with manipulating light. So on the right is a picture of sort of a thin film of liquid crystal. And you have polarized light that's being shined through the bottom of it. So you're just looking at what gets through. And then based on the orientation of the molecules, these things act as sort of like polarizers, like Polaroid sunglasses, based on the orientation. So that's why some of the light gets blocked, because the light is already polarized when it comes through. And so there's lots of applications for this, LC display, stuff like that. This is an actual example of what one of these molecules looks like. Again, it has this, it's rigid and it has this sort of elongated structure to it. And these were discovered accidentally by this guy, botanical physiologist Friedrich Reinitzer. He was studying carrots, apparently. And I guess what shows up in carrots is something called cholesteric benzoate. And so he was doing some experiments, and it turned out that he didn't really understand this, so he says, well, what he came up with is that it has two melting points. So it first melts into a cloudy liquid at a certain temperature. And then if you continue increasing the temperature, it would melt again and then become clear. And so the cloudy liquid was actually a liquid crystalline phase. He had no idea what was going on, so he got help from physicists. And it turned out that the cloudy fluid was crystalline. And then after this, the first guy did not pursue liquid crystals. Yeah.
He has a question. Have you tried this experiment with carrots?
No, I'm not even sure how I could. I mean, that's quite high temperature. So the first guy just dropped it as more of a physicist type of problem to look into, but he stuck with it for many years to come. So it's a meso-phase of matter. So it has what's called a partial order. So like a crystalline solid, is very ordered because the atoms are kind of rigidly held in place. Whereas in the case of liquid crystal, they can slide around, but the local orientation has to kind of obey its neighbors, or at least somewhat agree with that. So this is sort of a simple intuition. So if you imagine the matchsticks of these molecules, and you want to jam them into a tight space, well, they have to line up in order to get them to fit. And then something that's more akin to a liquid crystalline phase, there's a bunch of kayakers. And so the kayaks have an elongated shape, and if you look at this, you can even spot some +1/2 defects. And so this is what we're trying to model and be able to simulate. So I was going to put in like a quick explanation for how the LC display works, but if everyone knows this, I can skip it. You want it? Okay. So, all right, flat panel monitor, LC display. You all know what Polaroid sunglasses do, right? Polarized light. Basically, light comes in, has all sorts of random directions to it. You give it a polarizing filter, sunglasses, and it just wipes out everything except for one direction. Okay, so that's the basic idea. And so the way that LC display works, or each pixel, if you will, is you have like some kind of rectangular region. This is where the pixel is, and then there's some liquid crystal molecules in that. And so these molecules act like a stack of polarizing filters. And so if you have the polarized light and you line up the filter to allow the light come through, nothing happens. But then if you put a bunch of filters and they gradually change the angle, then it's still able to let the light through. But these things, again, because they have some nice properties, they respond to electric fields. And so if you turn on the electric field, it makes them sort of change the direction, and then that just lets the light come through completely. And so the way you take advantage of this is that you polarize the light coming in, you have another filter that's at 90 degrees. And so that will block the light completely, unless you let these things act as this sort of stack of filters. That's basically how it works. And then the real thing is, okay, for each of the colors, red, green, blue, you have one of these little blocks of liquid crystal, and they're controlled by electric fields to kind of tune the amount of light that comes through. Anyway, so that's how it works. Some other examples of where liquid crystals show up is in materials. So you can design or create some kind of soft material that has essentially liquid crystal molecules embedded into it, and that gives it kind of an anisotropic response. And so you can cause these things to bend in sort of non-trivial ways. Another application of liquid crystals doesn't have anything to do with liquid crystals, it's actually modeling what's called active matter. So here's a bunch of bacteria, and each of the bacterium looks like an elongated ellipsoid. And so if you have a bunch of these together, then when they actuate themselves and try to swim around, you can actually model that using liquid crystal types of equation. So there's lots of sort of motivation for why you would want to do this that have lots of potential applications. Okay, so how do you actually model this stuff? So in principle, I'm going to have all these liquid crystal molecules, and people do molecular dynamics on these types of things to try to model them from first principles. But it's not really tractable for what we want to do. And so, and personally, I was never very good at chemistry, and I don't want to have to look at a bunch of chemistry diagrams. And so I'm going to do what any reasonable person would do would be to run away from this. Run away. And you have to forgive the picture. There should be more, but I got tired of mixing these molecules. So you keep running, and it's a little faint up here. So you keep running until they start. You get so far away that the molecules look like line segments. And so you can't see the molecular structure anymore, but you can see this anisotropic aspect. And then, okay, we're just going to model it with a line field. So instead of a vector field, we have a field with line segments, if you will. So at each point in the domain, we're going to have some element from, say, RB2, if we're in 3D. And so this is basically a headless vector. And I'll say a little bit more about where this comes from next. So what we're really trying to do is do some kind of like ensemble or probabilistic averaging. So suppose these line segments are my representing the orientation of my molecules, and they're just sort of like randomly distributed. And looking at just sort of a single region, small region of space, and then I can, in principle, have the probability distribution for the angle that these molecules have. And so that's what's kind of illustrated here. These things are sort of oriented roughly in this general direction, so the probability is highest along that direction. But because these are headless vectors, if I rotate them by 90 degrees, it should have the same probability. This is like a symmetry condition. And okay, it's a probability, so it should integrate to 1. And so then you can say, well, maybe we can do some averaging to get like a useful so-called order parameter. And so P is going to be a unit vector that's defined on the circle, and I'm just going to compute the first moment with this. But because of this symmetry, if I shift things by pi and then use this property, doing this, I actually have a minus sign because P is a vector, not a headless vector. So if I rotate, I change the direction. But then this is basically the same as that, except there's a minus sign. So I can move it over, so it must be 0. So the average is 0, so you don't get any useful information. You have to go to the so-called second moment, basically computing the covariance matrix, this probability distribution. And so that's what you do. You do the same. That was all kind of posed in 2D. This is 3D. And in principle, at each point in space, you would have a whole probability distribution to compute. We don't really do that. This is just sort of deriving the order parameter. And then in the end, you get this matrix M, which traces 1. And then if you, for example, suppose you had a uniform distribution of the molecules, so they're just completely randomly pointing in every direction, then the M you get is just a multiple of the identity. So this would be an isotropic state. So it's not nematic or ordered in this case. So for mathematical simplicity, here this is what we want, but the trace is has this fixed value of 1. So to simplify it, we subtract off a multiple of the identity. That gives the so-called Q matrix, the Q tensor. And Q is symmetric and traceless, and so that's the kind of normalization aspect. And so this is how we can model a line field. And so if we're in 3D, and depending on the properties of Q, it's uniaxial if it has this form, and this N would be somehow like the average direction that the molecules would face in. And so then you can look at, and so the S here in this case has the following interpretation. So this N is like this averaged N, and then S is sort of measuring how well aligned are the individual molecules with the average N. So, and that's called the degree of orientation. And so if S is close to 1, they're well aligned. If it's 0, that's a defect. That means there's no net direction. And if it's -0.5, they're just orthogonal. So let me describe a little bit about defects, because that's sort of an important aspect of liquid crystals. So any kind of fibrous material, something that has this sort of line field aspect, will have defects. So this is sort of just some images of that, and then kind of cartoons of what the line segments would look like. And so when you have a defect, it has a so-called degree associated with it. So this is a -1 degree defect, +1. But you can also have half integer defects. This is a +1/2, -1/2 degree defect. And the way that's defined is through basically the winding number. So here's a +1/2 degree defect. You basically follow a path around where the defect, where the singularity is, and you just measure how many rotations the line segment goes through. So this one goes through 180 or pi, and you normalize by 2 pi, so that's why it's a half. And then this way, it just bends back the other way, so that's why the change in sign. So this is a -1/2 degree defect. And then this would be a +1 degree defect, so it has a full 2 pi rotation. This is -1, it just is rotating the opposite direction. You can go higher, okay, +3/2, -3/2. As you go higher, the vector field or this line field will get more kind of erratic. So that's how you classify defects. And one nice thing about the Q-tensor model is you can represent all of these defects, even the half integer ones. And the main issue that shows up, like this is the -1/2 degree, this is +1/2. If you try to give it an orientation where you want a vector field to kind of identify with the line field, you can't do it in a consistent way. You'll have some kind of discontinuity that's unavoidable. For an integer defect, you can always do that. All right, so anyway, so we have this Q tensor. So this is a space of symmetric traceless tensors. Because it's coming from a probability distribution, its eigenvalues have some bounds. In general, it has a biaxial form. However, most of the time, for various reasons, it will be uniaxial. It just means it has two equal eigenvalues, and it'll look like this. And when I show plots of like simulations, things like that, the N here is going to be what's used to kind of visualize what the Q tensor is doing. Because otherwise it would be kind of too high dimensional to see what's really happening. Okay, so. All right, so how do you, okay, so we basically have a way to represent the liquid crystal state. So we need to have some other stuff that comes into the model, and this brings in the so-called Landau energy. And so, for example, if we're gonna look for equilibrium states, we would look for minimizers of this. And so this has sort of several pieces. One of those is the elastic energy. So this involves gradients of Q. And these are a bit more complicated. It's just using indices and whatnot. You could just focus on the first guy. This is just grad Q squared. And so this is measuring how much the molecules sort of change orientation as you move through the liquid crystal. There's other terms that show up here based on whatever the material properties are of the liquid crystal. One of those involves the so-called cholesteric twist. And so this has the so-called rho-wise curve of Q that shows up. All right, the next piece is, so that's the psi, is the so-called bulk potential. And so this is a quartic polynomial in Q, and this is connected to the so-called Nematic to isotropic phase transition. And what that does is it kind of controls the uniaxiality of psi, or uniaxiality of Q. So minimizers of this are uniaxial. And this ends up being heavily penalized in the energy. And so the Q tensor will be uniaxial almost everywhere in the domain except the defects. So, okay. And then the other main piece has to do with these boundary integrals. So omega is the domain of the liquid crystal, and then gamma is just the boundary of that. And so on the boundary, we have so-called surface energy term. So remember I had this, my line field, which was going to be basically n times n. And so what this is kind of illustrating would be like the eigenframe of the Q. And so n being the main dominant eigenvector. And so based, again, on the properties of the material, or the surface anchoring, or like the boundary conditions that are being imposed, we may want the main director, or n, to be normal to the surface, or we want it to be tangential or planar. And depending on what you want, these are the terms that you would add. So if you want normal, you would only have this piece, where you have Q gamma taking on this uniaxial form. That's the surface normal vector nu. Or you have planar anchoring, and then this is trying to drive Q to a perpendicular state or a planar state. So this pi is just the surface projection, tangent space projection operator. But anyway, you put these into the energy, they're effectively penalized. Okay, so I wanted to show some simulations of another application of liquid crystal. So this is coming from liquid crystal shells. So the thing that's in blue is just an isotropic fluid, say water, and there would be water outside of this. And then in between, you have liquid crystal molecules. And these have a cholesteric property, which causes them to twist. And what happens is when you shine, again, polarized light, through these things, they have sort of interesting reflection properties. And one of the applications of this is to do special coatings of surfaces where when these things reflect these patterns, if you can sense that, you can use it as a way to kind of mark like buildings or architecture with sort of like hidden, I don't know, messages or signals in a way to kind of take advantage of. Another application is for anti-counterfeiting. So apparently these patterns, you cannot reproduce them. So you can create basically a unique pattern that can't be, cloned or whatever. And then you attach this to whatever object you want to be sort of authenticated. So here the energy, it looks like this. You can rewrite it in the form I showed before, just by playing around with the different constants. Again, there's this twist parameter tau naught that shows up. This was done by my first PhD student. The reference is there. Some other references as well. So let me just show some simulations of this. So here we have a liquid crystal device that's essentially just a slab. So you have two parallel plates with this cholesteric liquid crystal in between. And then the first column here is just basically the initial condition that we use in our simulation. And then here is essentially the equilibrium state that we compute. The color is just the director n coming from the Q tensor. That's the dominant eigenvector, dotted with the normal vector of the slab. So you can see the color scale below. And so so one of the properties of these cholesteric liquid crystals is that, well, the director, it forces it to kind of rotate. And so as you move through the domain, the director keeps rotating, and that's why you get these stripe patterns show up. And when they do experiments, they see these same kind of fingering patterns show up. And so we have homeotropic, this is the normal anchoring stuff, and this is the planar anchoring. This is the shell case. So, again, so each row, so this is like very little twist and then increasing twist, meaning that you get more and more stripes through the domain. Against the initial condition, normal anchoring, planar degenerate anchoring. And you also see patterns sort of similar to this as in the experiments. The experiments are actually a bit finer, so the twist is a bit higher, you get more stripes. So this was the front, and then just looking at the top, you can see these sort of interesting spiral pattern at the top. And it's similar between normal anchoring and planar anchoring, although there is a little bit of difference in how the color comes up. So one thing about these cholesteric shells is that you have to deal with buoyancy effects, because it's really hard to try to make the liquid crystal have the same mass density as, say, water. And so usually these things kind of get off-centered, and that affects the patterns that show up. So for example here, since it floats up, the thickness at the top is quite thin, and so there's not really a lot of room for the liquid crystal molecules to rotate around. So that's why you don't get these stripes at the top, but they're more concentrated to the bottom. Of course, when you have higher twist, you can fit in, more, into that small space of rotation. This is essentially doing the same thing, but giving a much more ridiculous initial guess. And so this is a non-convex problem. You're trying to minimize a function that's not convex. So it has multiple minimizers. And so this just picks up other minimizing states. And you can see these different kind of defect patterns that show up in the color. And this is kind of an interesting one. And this was sort of reminiscent of what, when we were talking to your colleague earlier, and she was doing, I think she was even doing planar degenerate anchoring in this case. And so that also had some, not hexagons, but some separate like patterns that came up that sort of reminded me of that. So one of the things that we wanted to point out in this paper, especially to like liquid crystal physicists, was that if you're not careful with, say, numerical parameters like, say, the mesh size, then you can compute things that really aren't physical. So these are just numerical artifacts. You know, if you have a much smaller, much finer mesh, you're not going to get something like this. So, whereas if you're not aware of this, you may think that, oh, well, this is actual physical manifestation. And also using different initial guesses, initial conditions can affect the kind of states. Because if we use an initial conditions kind of match to what we expect, we don't get this. These like little triple points. So that was one of the lessons here, if you will. All right, so for the next part of the talk, so one thing that people have been looking into for doing liquid crystals is to sort of manipulate them by putting in colloids. And colloids are just solid objects kind of immersed into the liquid crystal. And what's convenient about this is that you can impose different boundary conditions on the colloid. So for example, here on this colloid, this is normal anchoring, because the line segments are pointing orthogonal to the surface, but on the other side, they're tangential. So you can kind of mix things up, and so that sort of augments what the liquid crystal state will be. And you can take advantage of this to make like metamaterials, in principle. This is another example. This is an actual experimental image of a bunch of colloidal spheres. And this little rope that goes around it, that's actually a line defect. So the point defects I showed before, that's for 2D, but if you're in 3D, those points become lines that kind of wrap around these colloids. And that affects, say, the properties, as well as how these things assemble, things like that. And so again, applications would be in metamaterials. So with my other student, we looked at doing a method for trying to model how these liquid crystal systems evolve in moving domains, because the colloids are moving. So I basically want to model, say, a liquid crystal domain omega that changes in time based on the motion of a bunch of colloidal particles. And the particles could have, whatever shape I want, although in the simulations, they'll just be disks or spheres. And so when I do this, I'm going to assume that the velocity of the colloids is prescribed. So that's given. And then on top of that, I'm going to extend the velocity just by solving Stokes. So essentially the velocity field is prescribed. And because it's prescribed, I don't have to sort of model the so-called full Barris-Edwards system. So that's why I say this is half of Barris-Edwards. The other half would be Nevius-Stokes with additional coupling terms for Q. So what does this involve? So this E here, that was the liquid crystal energy that I showed before. This is just the variational derivative. The hat is just taking the traceless part. This is just the advective material derivative of Q. And then you have extra stuff showing up in the so-called Barris-Edwards term. And without getting into a lot of details, so the Q is sort of representing this kind of material state, right? So you have these like molecules that are oriented. So if the fluid that's carrying these molecules somehow rotates, these molecules also have to rotate in order to be sort of correct in the continuum mechanics sense. To do that properly, you have to add this stuff. Mainly this first piece. And this is connected to what's called the co-rotational derivative. Anyway, a little bit of a mess, but it's not too bad. You go through, you can write down the full strong form PE. I'm not saying you should try to read this. It's a bit of a mess. But I mean, that's in principle what it looks like. It's very much akin to doing, say, Allen-Kahn with an advective derivative. But then you have a Robin boundary condition, and then there's some nonlinear stuff that comes along. Okay. So then for doing the analysis, and I'm not going to go through all the details of this. People here taking PDE? Okay. Everybody knows what a weak formulation is? Well, yes, I know you do. Who else knows what a weak formulation is? Nobody? No one wants to say. Okay, well, anyway, so you have a strong form PDE, you can multiply by the test function, integrate, do all this typical stuff. You define a very bunch of bilinear forms. For example, this has to do with the surface anchoring, this has to do with including the elastic energy, so on and so forth. And then you can basically just rewrite PDE in this way. And so this is my transport term. So time derivative of Q and this Barrett-Edwards piece. This is just rewriting the advective term in a convenient way for the analysis. And then you have the so-called elliptic part. This is where the elastic energy is. And then you have some nonlinear stuff. So then, so you can show that this system has a solution by sort of more or less standard PDE techniques. So to get a numerical method, I'm going to discretize in time first. And I'll just give the highlights here. So I have a domain that's changing. So if I'm going to discretize in time, I'm going to run into a problem of trying to compare the solution between two different time steps because the domain has changed. And so the way to deal with that is, so I have my domain at time tn minus 1 and then at time tn. And so I need to be able to compare the solution Q that's on those, defined on those different domains, because I have to be able to take a time derivative. And so to do that, I need to have some kind of extension of, say, Q on the previous time step. And so in order to make sense of that, then I have to make sure that the future domain does not move too far from the old domain. That's all this says, that it sort of stays within a nice little close neighborhood of the previous domain. And if you do that, then you can do the extension without any problem, and you can compute this in a meaningful way. So anyway, you put that in, so this is the time discrete variational formulation, which is exactly what I had before, except now I have this time discretization comes in. So I'm now trying to solve this equation, Gn equal to theta n. This is a variational problem at each time step. So this, I thought I would skip some of the details on, although maybe Giordano would like to know.
I can ask later.
Say what?
I can ask later.
That's true. That's true. So maybe I'll do that. But okay, so you can do it. You can show there exists a solution to this using some techniques. You can show that there exists a unique solution to this, provided the time step is small enough. This is, I'm going to skip this. You can also get an energy estimates, and you can even avoid having an exponential dependence on the time. That just takes advantage of the double well. Anyway, so since I have a moving domain that will have multiple colloids in it, and so it's convenient to use, say, an unfitted method. If I'm doing finite elements and I have a moving domain, I could either mesh the domain, but then I have to deal with the deformation of the mesh, and this is kind of a problem. Or you can use an unfitted approach where you basically have a fixed grid, and then you just track the motion of these things in, say, a convenient way. So the highlights are the mesh does not conform to the domain, so you can handle the geometry pretty easily. Of course, you have to do some extra stuff to make the method work for the cut elements. And you also have to deal with some extra implementation and stuff. So Alright, so how does this work? So I have a fixed background mesh. Lagrange finite elements, so nothing fancy. And then I'm going to track the domain using level set functions. So this is a well-known technique. So wherever the level set function is negative is where the domain actually is. And then, so the black is the actual boundary of my domain, and then I extend, some amount delta in either direction to have like a neighborhood like that. Okay. And these will actually use discrete level set functions, again, using Lagrange finite elements to represent that. And then, again, without getting into all the technical details here, I'm doing finite elements. So when I solve the problem, say at each time step, I need to solve it on, say, some subset of elements. Those are the ones that are grayed. And so again, black is where the actual boundary is, but I have to extend it just a little bit away from that in order to do this time derivative properly. The rest of this stuff is just some technical considerations about how the domain changes in time. It's just a temporal coherence I had mentioned before. So the one issue that shows up has to do with, so when this domain cuts through the mesh, the action of the elements or the basis functions on the outer nodes has a very weak effect on the solution. Because in principle, I don't really care what's happening out here. The solution is only here. But if I cut the mesh like this, the basis function that's active here has some influence on that. But it's very weak because it's only just barely cutting through there. And so that leads to ill conditioning of the linear system that you have to solve. So there's a way to fix that, which uses what's called facet stabilization. You basically add some extra jump terms on the facets in that neighborhood, and that kind of helps control the ill conditioning. The finite element space for the Q tensor is just doing Lagrange basis functions again, and then you just do it for each component. So you can take the space of symmetric traceless matrices, and in 3D, the dimension of that space is 5. So there's 5 unique basis matrices you can expand, and so that's how I represent the numeric solution. So you do that, you plug all that in. So that means for a given tensor capital Q, I have a lowercase vector Q solution, which has 5 components. Okay, so then the finite element scheme is you basically take, you make everything discrete, you put H's everywhere, and then you have to add the stabilization term to the problem, and that's this facet stabilization to avoid this issue of cut elements. So then you get this capital AH, and so that shows up here. All of the other estimates I showed before essentially extend to this as well, without going into the details. In this case, the energy estimate for the error is exponential in time. It wasn't clear to me to see how to avoid that, because you take it different. And then this is the error estimate. Since we're doing backward Euler, we're basically limited to order delta t, which isn't, you can avoid that. You could extend this analysis to do like BDF2 or something like that to get higher order accuracy. This is just a basic convergence check, just to make sure that things are converging like they should. The rates look a little bit better than what you would expect because it's backward Euler. Perhaps if I took this further, kept refining, I would see that more. Okay, so then I want to show a bunch of examples, some simulations to illustrate the model. So the way this is going to work, so these are just 2D simulations. I want to take piecewise quadratic finite element space for the QH, as well as for the level set function. I want to use Taylor Hood elements, solve Stokes, to get my extended velocity field. All right, so this first one, so I have its domain. I have 2 colloids that are just going up and down. And so on the left here, this is normal anchoring. Oh no, all of this is normal anchored. Now I do a planar on the next one. So here's a movie of the simulation. So the line segments here, when I solve the problem, I have Q as my solution, and then I do an eigen decomposition for Q as a post-process to visualize what the director looks like. And so here we're doing normal anchoring, and so you can see the line segments are normal to the surface, and you can see a -1/2 degree defect is at either opposite end of the colloids. So that's for normal anchoring. If you do the same problem with a planar, it's a little bit different. So here the -1/2 degree defects are on the sides. Again, opposite. But you can also see this kind of switching phenomena that happens to the director in the middle based on where the colloids are. And in a lot of the applications of liquid crystals, they want to have something like that. They want to have like some kind of immediate switch because that sort of adds functionality to the liquid crystal device because you can go to switch between two different states in an easy way. So this is the same problem, but just moving left and right now. So again, you can see the -1/2 degree defects. And then the defects, do interact a little bit here. And again, you can see this kind of switching of the state as it goes back and forth. And so that was normal anchoring and planar. This one doesn't switch so much. It's more of a kind of gentle variation between the two. And then for the last simulation, these are two circles moving, around each other. We'll start with normal anchoring. And again, you can see this sort of like switch in the interior state as they move around. And again, these -1/2 degree defects follow the colloids around. Yeah.
What is the boundary condition of the outside?
It's just I picked a Q such that its dominant eigenvector is horizontal. So you can see that here. And then the initial condition was, well, it starts vertical. So that's why there's a little bit of a transition at the beginning. The color for the line segments is the norm of Q. The color for the background field is just the velocity, magnitude of the velocity field. And then for the planar case, and this also has kind of a switching state that shows up. All right, so I will conclude now. So we have an unfitted FEM for doing time-dependent Landau Dijen. And we extended some of the unfitted FEM techniques to doing, nonlinear parabolic equations. So this gives a nice way to investigate defect dynamics and sort of design of LC devices even. All these simulations were done with NGSolve with this add-on package. That's what allows you to do the unfitted stuff. And then some extensions of this would be to try to look at the more coupled problem of actual self-assembly of the colloids. So try to actually have the velocity field be involved as a separate solution, and even doing some kind of optimal control of the assembly of these colloidal objects. So with that, I thank you again for your attention, and I will stop.
we have questions for the speaker?
Yeah.
Yeah, I have a question about the moving boundary part.
Yeah.
You are using the level set method.
Yeah.
So I want to double check about your technique. So because the moving boundary, when it moves from Tn to Tn plus 1,
Yeah.
so basically you are losing some grid points and introducing some new grid points.
Right.
So for example, when you introduce a new grid points, you don't have information on that grid points. But
Yeah, but we actually do, and it's because of that extension. So when we solve it, we don't just solve in the domain, we actually solve a little bit outside of it. So that's what I was talking about with this extension layer.
okay. Oh, yeah, sure. Yeah.
So, I mean, this was a classic problem with the immersed boundary method,
Mm-hmm.
where if, as the immersed boundary would cross grid points, you get these ringing effects and stuff like that.
So basically, it's like a technique of extension in normal
Well, yeah,
direction.
right, so that facet stabilization, that effectively extends the solution.
Okay, thank you.
More questions? Question, comment? I have a question.
Yeah.
Is when you present the model with the fluid part, with only half the fluid part,
Yeah.
so you keep the stretching effect, that you said that are the...
Yeah, the co-rotational
So
version.
my question is, does that equation has an energy law? Because usually to cancel that, you use the term that came from Navier-Stokes.
Yeah, right. Well, yes, you can. I mean, we got an energy estimate.
Okay.
Right.
So what do you do with that term? Do you move to the other
Well-
side and you control it?
Yeah, basically. I mean, the thing is, yeah, so the B here.
Yeah, the big...
So since B is prescribed, well, S and W.
Oh, okay, because
Right.
it's there. Okay.
So then these are just coefficients, right?
I see that.
And this is all lower order term. There's no gradients in Q here. So you can control it. And actually the double well potential, the quartic term, helps to control even this piece.
So I have another question about
Yeah.
the double well potential. So do you use some coefficient in front of it?
Yes.
And do you need that coefficient is large or something like this?
Well, I mean, the time step has to be small relative to that, right? So, where is this? Well, this isn't non-dimensionalized yet, but, where is this? Okay, I guess.
It's okay, you don't need to...
Yeah, so this is 1/8 squared.
Oh, okay, so you
Yeah.
need a large, 1 over something small.
You need the time step to be sufficiently small, and it's gonna be affected by that, yeah.
Thank you.
Yeah.
Do
And
we
in
have,
these simulations, eta was 0.1, so 1/8 squared.
do we have more questions?
Yes.
Are fingerprints line fields? Like, can you study fingerprints?
I mean, one thing that's interesting about the Q stuff is that, and this is sort of connected to that tissue project model I was talking about with you earlier, was you can use Q to model other things. Basically, you can use it to model anything that's anisotropic, right? Because, the line, like if you had a material, like an elastic body that had, fibers in it, you could model that anisotropy with a Q function that has its form. And the line field, you could even possibly look at a data-driven approach to try to fit a Q, to that. Actually, I hadn't thought about that. It's kind of interesting. What's my Q?
Yeah.
Any other questions or comment or suggestion? If not, let's thank the speaker again. Thank you very much.